I am Neha from MSc Chemistry, Unit 1st, Chapter Solution, Class 12th. Almost all processes in body occur in some kind of liquid solution. In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass mixture of copper and zinc are quite different from those of German silver. Mixture of copper, zinc and nickel or bronze. Mixture of copper and tin. 1 ppm of fluoride ion in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottled, and high concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injection are always dissolved in water containing salt at particular ionic concentration that match with blood plasma concentration and so on. In this unit, we will consider mostly liquid solution and their formation. This will be followed by studying the properties of the solution like vapor, pressure and colligative properties. We will begin with types of solution and then various alternatives in which concentration of a solute can be expressed in liquid solution. Types of solution. Solution are homogeneous mixture of two or more than two compounds. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. Solvent determine the physical state in which solution exists. One or more components present in the solution other than solvent are called solute. In this unit, we shall consider only binary solution consisting of two components. Here, each component may be solid, liquid, or in gaseous state and are summarized in table. Gaseous solution. Gas gas mixture of oxygen and nitrogen gas. Liquid in gas chloroform mixed with nitrogen gas. Solid in gas camphor in nitrogen gas. Liquid solution. Gas in liquid oxygen dissolved in water. Liquid in liquid ethanol dissolved in water. Solid in liquid glucose dissolved in water. Solid solution. Gas in solid solution of hydrogen in palladium. Liquid in solution amalgam of mercury with sodium. Solid in solid copper dissolved in gold. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively we can say that the solution is dilute. Relatively very small quantity of solute, or it concentrated. Relatively very large quantity of solute. But in real life, these kinds of description can add to lot of confusion. Thus, the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of solution quantitatively. Mass percentage. The mass percentage of component of a solution is defined as mass percentage of a component, mass of the component in the solution by total mass of the solution into 100. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram glucose is dissolved in 90 gram water, resulting in a 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical application. For example, commercial bleaching solution contain 3.62 mass percentage of sodium hypochlorite in water. Volume percentage. The volume percentage is defined as volume percentage of the component, volume of the component by total volume of the solution into 100. For example, 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of the solution is 100 ml. Solution containing liquid are commonly expressed in this unit. For example, a 35% volume by volume solution of ethylene glycol and antifreeze is used in cars for cooling the engine. At this concentration, the antifreeze lowers for the freezing point of water to 255.4 K in minus 1.76 degrees Celsius. Third, mass by volume percentage. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 ml of the solution. Parts per million. When a solute is present in trace quantities, it is convenient to express concentration in ppm. Parts per million is equal to number of parts of the component by total number of parts of all the component of the solution into 10 to power 6. As in the case of percentage, concentration in parts per million can also be expressed as mass to mass, volume to volume, and mass to volume. A liter of seawater, which weighs 1030 gram, contain about 6 into 10 to power minus 3 gram of dissolved oxygen O2. Such a small concentration is also expressed as 5.8 gram per 10 to power 6 gram 5.8 ppm of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of μg meter liter inverse or ppm. Mole fraction. Commonly used symbol for mole fraction is chi, and subscript used on the right hand side of chi denotes the component. It is defined as mole fraction of a component, number of mole of component by total number of moles of all component. For example, in a binary mixture, if the number of moles A and B are Na and Nb respectively, the mole fraction of A will be chi A is equal to Na by Na plus Nb. For a solution containing I number of components, we have chi is equal to Ni by N1 plus N2, so on. Ni is equal to Ni summation of Ni is divided by summation of Ni. It can be shown that in a given solution, sum of all the mole fraction is unity. X1 plus X2 plus so on plus X1 is equal to 1. Mole fraction unit is very useful in relating some physical property of solution, say vapor pressure, with the concentration of the solution, and quite useful in describing the calculation involving gas mixture. Molality. M is defined as the number of mole of the solute per kilogram kg of the solvent and is expressed as molality mass of solute by mass of solvent in kg. For example, 1.00 mole kilogram inverse or 1.00 meter solution of KCl means that 1 mole 740.5 gram of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solution has its own merits and demerits. Mass percentage, ppm, mole fraction, and molality are independent of temperature, whereas molarity is a function of temperature. This is become volume depend on temperature and the mass does not. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of the solvent at a specified temperature. It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in liquid. Solubility of a solid in a liquid. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene and anthracene don't. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar don't. It is observed that polar solute dissolve in polar solvent and non-polar solutes dissolve in non-polar solvent. In general, a solute dissolves in a solvent if the intermolecular interaction are similar in two, or we may say dissolve like. When a solid solute is added to the solvent, some solute dissolve and its concentration increase in solution. This process is known as dissolution. Some solid particle in solution collide with a solid particle and get separated out of solution. This process is known as crystallization. A stage is reached when the two processes occur at the same rate. Under such condition, number of salt particles going into solution will be equal to the solid particles separating out, and a state of dynamic equilibrium is reached. Solute plus solvent gives a solution. At this stage of concentration of a solute in solution will remain constant under the given conditions. Temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is the saturated solution and contain the maximum amount of the solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substance. In addition to these variable two other parameters, temperature and pressure also control this phenomena. Effect of temperature: the solubility of a solid in a liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 1.10. This being dynamic equilibrium must follow Le Chatterjee principle. In general, if in a nearly saturated solution, the dissolution process is endothermic. Delta sol H greater than 0, the solubility should increase with rise in temperature, and if it is exothermic, delta solution H less than 0, the solubility should decrease. These trends are also observed experimentally. Effect of pressure. Pressure does not have any significant effect on solubility of solids in liquid. It is so because solids and liquid are highly incompressible and practically remain unaffected by changes in pressure. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is the it is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas is highly soluble in water. Solubility of gas in liquid is greatly affected by pressure and temperature. The solubility of gas increases with increase of temperature. For a solution of gases in a solvent, consider a system as shown in figure 1.1a. The lower part of solution and the upper part is gaseous system at pressure P and temperature T. Assume this system to be in a state of dynamic equilibrium. Under this condition, rate of gaseous particle entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. Figure 1.1b. This will increase the number of gaseous particle per unit volume over the solution and also the rate at which the gaseous particles are striking the surface of solution to enter it. The solubility of gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution and thus its solubility increase. Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is known as Henry law. The law states that at constant temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Dalton, a contemporary of Henry also concluded independently that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. If we use the mole fraction of a gas in the solution as a measure of its solubility, then it can be said that the mole fraction of a gas in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used from Henry's law states that the partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas chi in the solution and is expressed as P is equal to Kh chi. Here Kh is Henry constant. If we draw a graph between the partial pressure of gas versus mole fraction of the gas in solution, then we should get a plot of type as shown in figure 1.2. Different gases have different Kh value at the same temperature. This suggests that Kh is a function of the nature of the gas. It is obvious from equation 1.11 that higher the value of Kh at a given pressure, the lower is the solubility of the gas in liquid. It can be seen from table 1.2 that Kh value for both nitrogen and oxygen increase with increase of temperature, indicating that the solubility of gas is increase with the decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold water rather than in warm water. Henry Law finds several applications in industry and explains some biological phenomena. Notable among these are to increase the solubility of CO2 in soft drink and soda water, the bottle is sealed under high pressure. Scuba divers must cope with high concentration of dissolved gases while breathing air at high pressure underwater. Increase the solubility of atmospheric gases in blood. When the divers come towards surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubble of nitrogen in the blood. This blocks capillary and create a medical condition known as bands, which are painful and dangerous to life. To avoid band as well as toxic effect of high concentration of nitrogen in the blood, the tank used by scuba divers are filled with air diluted with helium, nitrogen and 32.1% oxygen. At high altitudes, the partial pressure of the oxygen is less than that the ground level. This leads to low concentration of oxygen in the blood and tissue of people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly. Symptoms of condition known as anoxia. Effect of temperature. Solubility of gases in a liquid decrease with rise in temperature. When the dissolved, the gas molecules are present in the liquid phase and the process of dissolution can be considered similar to condensation. And heat is evolved in this process. We have learned in the last section that dissolution process involve dynamic equilibrium and thus must follow Le principle. As dissolution is an exothermic process, the solubility should decrease with increase of temperature. Vapor pressure of liquid solution. Liquid solution are formed when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Solution of gases in liquid have already been discussed in section 1.3.2. In this section, we shall discuss the solution of liquid and solid in a liquid. Such solution may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the property of only binary solution. That is the solution containing two components, namely the solution of liquid in liquid and solid in liquid. Vapor pressure of liquid solution. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be partial vapor pressure of two components 1 and 2 respectively. These partial pressure are related to the mole fraction chi1 and chi2 of the two component 1 and 2 respectively. The French chemist Francois Martrault 1886 gave the quantitative relationship between them. The relationship is known as the Rolle's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. Thus, for component 1, P1 directly proportional to chi1, P1 is equal to P naught 1 chi1, where P naught 1 is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, P2 is equal to P naught 2 into chi2, where P naught 2 represent the vapor pressure of the pure component 2. According to Dalton law of partial pressure, the total vapor pressure P total over the solution phase in the container will be the sum of the partial pressure of the components of the solution and is given as P total is equal to P1 plus P2. Substituting the values of P1 and P2, we get P total chi1 into P naught 1 plus chi naught into P naught 2 is equal to 1 minus chi naught into P naught 1 plus x2 into P naught 2 is equal to P naught 1 plus P naught 2 minus P naught 1 into chi 2. Following conclusion can be drawn from equation 1.16. Total vapor pressure over the solution can be related to the mole fraction of any one component. that total vapor pressure over the solution varies linearly with the line mole fraction of component 2. Depending on the vapor pressure of the pure component and 1 and 2 total vapor pressure over the solution decrease or increase with the increase of the mole fraction of component 1. A plot of P1 and P2 versus the mole fraction chi1 and chi2 for a solution gives a linear plot as shown in figure 1.3. These lines 1 and 2 pass through the points for which chi1 and chi2 are equal to unity. Similarly, the plot line 3 of P total versus chi2 is also linear. Figure 1.3, the minimum value of P total is P1 and the maximum value is P naught 2. Assuming that component 1 is less volatile than component 2. P naught 1 less than P naught 2. The composition of vapor phase in equilibrium with the solution is determined by partial pressure of the component. If Y1 and Y2 are mole fraction of the component 1 and 2 respectively in the vapor phase, then using Dalton law of partial pressure, P1 is equal to Y1 into P total, P2 is equal to Y2 into P total. In general, Pi is equal to Vi into P total. Rolle's law as a special case of Henry law. According to Rolle's law, the vapor pressure of a volatile component in a given solution is given by P1 is equal to chi1 into P1 not 1. In the solution of a gas in a liquid, one of the component is so volatile that it exists as a gas, and we have already seen that insolubility is given by Henry law, which states that P is equal to Kh into K. Rolle's law as a special case of Henry's law. According to Rolle's law, the vapor pressure of a volatile component in a given solution is given by Pi is equal to chi into Pi naught. In the solution of gas in a liquid, one of the component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to Kh into chi. If we compare the equation from Rolle's law and Henry's law, it can be seen that the partial pressure of the volatile component or gas is directly proportional to the mole fraction in solution. Only the proportionality constant Kh differs from P naught 1, thus Rolle's law becomes a special case of Henry's law, in which Kh becomes equal to P naught 1. Vapor pressure of solution of solid in liquids. Another important class of solution consists of solids dissolved in a liquid, for example sodium chloride, glucose, urea and cane sugar in water, and iodine and sulfur dissolved in carbon disulfide. Some physical properties of this solution are quite different from those of pure solvent. For example, vapor pressure liquid at a given temperature vaporize and undergo equilibrium condition. The pressure exerted by the vapor of the liquid over the liquid phase is called vapor pressure. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature in the solution. The surface has both solute and solvent molecule, thereby the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced, thus the vapor pressure is also reduced. The decrease in the vapor pressure of the solvent depends on the quantity of non-volatile solute present in the solution irrespective of its nature. For example, decrease in the vapor pressure of water. For example, decrease in the vapor pressure of water by adding 1.0 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1.0 mole of urea to the same quantity of water at the same temperature. Rolle's law in its general form can be stated as for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of the solvent, K1 be its mole fraction, P1 note be its vapor pressure in the pure state. Then according to Rolle's law, P1 directly proportion Chi1, P1 is equal to Chi1 into P naught 1. The proportionality constant is equal to the vapor pressure of pure solvent. P naught 1, a plot between the vapor pressure and the mole fraction of the solvent is linear. Ideal and non-ideal solution. Liquid solution can be classified into ideal and non-ideal solution on the basis of Rolle's law. The solution which obey Rolle's law over the entire range of concentration are known as ideal solution. The ideal solutions have two other important property. The enthalpy of mixing of the pure component to form the solution is 0 and the volume of mixing is also 0. Delta mix H is equal to 0, delta mix V is equal to 0. It means that no heat is absorbed or evolved when the components are mixed. Also, the volume of solution would be equal to the sum of volumes of the two components at the molecular level. Ideal behavior of the solution can be explained by considering two components A and B in pure component. The intermolecular attractive interaction will be of types A and BB, whereas in the binary solution, in addition to these two interactions, AB type of interaction will also be present. If the intermolecular attractive force between the A and BB are nearly equal to those between AB, this leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromothane and chloroethene, benzene and toluene, etc. falls into this category. Non-ideal solution. When a solution does not obey Rolle's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of such a solution is either higher or lower than that predicted by Rolle's law. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Rolle's law. The plot of vapor pressure as a function of mole fraction for such solution are shown in figure 1.6. The cause for this deviation lie in the nature of interaction at the molecular level. In case of positive deviation from Rolle's law, AB interaction are weaker than those between A or BB. In this case, the intermolecular attractive force between the solute-solvent particles are weaker than those between the solute-solute and solvent-solvent molecule. This means that in such solution, molecule of A or B will find it easier to escape than in pure states. This will increase the vapor pressure and result in positive deviation. Mixture of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecule get in between the host molecules and break some of the hydrogen bonds between them. Due to the weakening of interaction, the solution show positive deviation from Rolle's law. In a solution formed by adding carbon disulfate to acetone, the dipolar interaction between solute-solvent molecules are weaker than the respective interaction among the solute-solute and solvent-solvent molecules. This solution also shows positive deviation. In case of negative deviation from Rolle's law, the intermolecular attraction forces between A and BB are weaker than those between AB and leads to decrease in vapor pressure resulting in negative deviation. An example of this type is the mixture of phenol and aniline. In this case of intermolecular hydrogen bonding between phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding. Phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone form a solution with negative deviation from Rolle's law. This is become chloroform molecules is able to form hydrogen bond with acetone molecule as shown. CH3 bond C double bond O H bond C chlorine. This decreases the escaping tendency of molecule for each component and consequently the vapor pressure decrease resulting in negative deviation from Rolle's law. Some liquid on mixing from azeotropes, which are binary mixture having the same composition in liquid and vapor phase and boil at constant temperature. In such case, it is not possible to separate the component by fractional distillation. These are two types of azeotrope called minimum boiling azeotrope, maximum boiling azeotropes. The solution which show a large positive deviation from Rolle's law form, form minimum boiling azeotropes at a specific composition. For example, ethanol water mixture obtained by fermentation of sugar on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition known as azeotrope composition has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solution that showed large negative deviation from Rolle's law. For maximum boiling azeotrope at a specific composition, nitric acid and water is an example in the class of azeotrope. This azeotrope has the approximate composition 68% nitric acid and 32% water by mass with a boiling point of 393.5 Kelvin. Colligative properties and determination of molar mass. We have learned in section 1.4.3 that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solution which are connected with this decrease of vapor pressure. These are relative lowering of vapor pressure of the solvent, second depression of freezing point of the solvent, third elevation of boiling point of the solution, fourth osmotic pressure of the solution. All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such property are called colligative property. Colligative from Latin co means all these properties. All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such property are called colligative property. Relative lowering of vapor pressure. We have learned in the section 1.4.3 that the vapor pressure of the solvent in solution is less than that of pure solvent. Rolle's established that the lowering of vapor pressure depends only on the concentration of the solute particle and it is independent of their identity. The equation given in section 1.4.3 establishes a relation between vapor pressure of the solute, mole fraction and vapor pressure of the solvent. P1 is equal to chi1 into P01. The reduction in the vapor pressure of solvent delta P1 is given as delta P1 is equal to P01 minus P1 is equal to P01 minus P01 into chi1. P01 into 1 minus chi1 knowing that chi2 is equal to 1 minus chi1. Equation 1.23 reduces to delta P1 is equal to chi2 into P1. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 1.24 can be written as delta P1 by me P01 is equal to P01 minus P1 by me P01 is equal to chi2. The expression on the left hand side of the equation as mentioned earlier is called relative lowering of vapor pressure and is equal to the mole fraction of the solute. The above equation can be written as P01 minus P1 by me P1 is equal to N2 divided by N1 plus N2. Since chi2 is equal to N2 by me N1 plus N2. Here N1 and N2 are the number of mole of the solvent and solute respectively present in the solution. For dilute solutions N2 less than N1, hence neglecting N2 in the denominator we have P01 minus P1 divided by P01 is equal to N2 by me N1 or P01 minus P1 divided by P01 is equal to W2 into M1 by me M2 into W1 where W1 and W2 are the masses and M1 and N2 are the molar mass of the solvent and solute respectively. From the equation knowing all other quantities, the molar mass of solute can be classified. Elevation of boiling point. The vapor pressure of a liquid increase with increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin. bracket start 100 degrees Celsius bracket close, because at this temperature the vapor pressure of water is 1.013 bar 1 atmosphere. We have also learned in the last section that vapor pressure of the solvent decreases in the presence of non-volatile solute. Figure 1.7 depicts the variation of vapor pressure of the pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent water. Thus, the boiling point of a solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared, as shown in figure 1.7. Similar to lowering of vapor pressure, the elevation of boiling point also depend on the number of mole of solute molecules rather than their nature. A solution of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let T naught be the boiling point of pure solvent and TB be the boiling point of solution. The increase in the boiling point delta TB is equal to TB minus T naught B is known as elevation of boiling point. Experiments have shown that for dilute solution, the elevation of boiling point delta TB is directly proportional to the molar concentration of the solute in a solution. Thus, delta TB in direct proportion M, or delta TB is equal to KB into M. Here M molality is the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality KB is called boiling point elevation constant or molar elevation constant. Ebullioscopic constant, the unit of KB is kg mole inverse volume of. Values of KB for some common solvent are given in table 1.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution is given by expression M is equal to W2 by M2 divided by W1 into 1000 into W2 by M2 into W. Substituting the value of molality in equation 1.30, delta TB is equal to KB into 1000 into W2 by M2 into W1. M2 is equal to 1000 into W2 into KB divided by delta TB into W1. Thus, in order to determine M2 molar mass of the solute, known mass of solute is known as known mass of the solvent is taken, and delta TB is determined experimentally for a known solvent whose KB value is known. KB value is known. Depression of freezing point. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. We know that at the freezing point of substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solvent, as is clear from figure 1.8. According to Rolle's law, when non-volatile solid is added to the solvent, its vapor pressure decreases, and now it would become equal to that of solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Let T naught F be the freezing point of pure solvent and Tf be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point delta Tf is equal to T naught F minus Tf is known as depression in freezing point. Similarly, to elevation of boiling point, depression of freezing point delta Tf for a dilute solution. Ideal solution is directly proportional to molarity M of the solution. Thus, delta Tf directly proportion M. Delta Tf is equal to Kf into M. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or molar depression constant or cryoscopic constant. The unit of Kf is kg mole inverse. Value of Kf for some common solvents are listed in table 1.3. If W2 gram of the solute having molar mass as M2 present in W1 gram of solvent produce the produces the depression in freezing point delta TF of the solvent. Then molality of the solute is given by the equation 1.31. M is equal to W2 by me M2 divided by W1 by me 1000. Substituting this value of molality in equation, delta TF is equal to KF into W2 by me M2 divided by W1 by me 1000. Delta TF is equal to KF into W2 into 1000 by me M2 into W1. M2 is equal to KF into W2 into 1000 divided by Kf into W1. Thus, for determining the molar mass of the solute, we should know the quantities W1, W2 and delta Tf along with the molar freezing point depression constant. The values of Kf and Kb, which depend upon the nature of the solvent, can be ascertained from the following relation. Kf is equal to R into M1 into Tf का square divided by 1000 into fuse H. Kb is equal to R into M1 into Tb का square by 1000 into delta vapor H. Here the symbol R and M1 stand for the gas constant and molar mass of the solvent respectively. Tf and Tb denote the freezing point and the boiling point of the vapor of the pure solvent respectively in Kelvin. Further, delta fuse H and delta vap represent the enthalpies for the fusion and vaporization of the solvent respectively. Osmosis and osmotic pressure. There are many phenomena which we observe in nature or at home. For example, raw mangoes shrivel when pickled in brine. Salt water, wilted flowers revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. If we look into these processes, we find one thing common in all, that is all these substances are bounded by membranes. These membranes can be of animal or vegetable origin, and these occur naturally such as pig's bladder or parchment, or can be synthetic such as cellophane. These membranes appear to be continuous sheet or films, yet they contain a network of submicroscopic holes or pores. Small solvent molecule like water can pass through these holes, but the passes of bigger molecule like solute is hindered. Membranes having this kind of property are known as semipermeable membrane. Assume that only solvent molecule can pass through this semipermeable membrane. If this membrane is placed between the solvent and solution as shown in figure 1.9, the solvent molecule will flow through the membrane from pure solvent to the solution. This process of flow of the solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side to solution side occurs. A semi-permeable membrane can be stopped if some extra pressure is applied on the solution. This pressure that just stops the flow of solvent is called osmotic pressure of the solution. The flow of the solvent from dilute solution to concentrated solution across a semi-permeable membrane is due to osmosis. The important point to keep in mind is that solvent molecules always flow from lower concentration to high concentration of solvent. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis. To stop the passage of solvent molecule through a semi-permeable membrane into the solution, this is illustrated in figure 1.10. Osmotic pressure is a colligative property as it depends on the nature of the solute molecule and not to their identity. For dilute solution, it has been found experimentally the osmotic pressure is proportional to the molarity C of the solution at a given temperature T. Pi is equal to CRT. Here pi is osmotic pressure and R is gas constant. Pi is equal to N square divided by V into RT. Here V is the volume of solution in liter containing N2 mass of moles of solute. If W2 gram of solute of molar mass M2 is present in the solution, then N2 is equal to W2 by me M2, and we can write pi into V is equal to W2 into RT divided by M2, or M2 is equal to W2 into R2 divided by pi into V. Thus knowing the quantity W2 T pi and we can calculate the molar mass of the solid. Measurement of osmotic pressure provide another method of determining molar mass of solids. This method is widely used to determine molar mass of protein polymers and other macromolecules. The osmotic pressure method has the advantage over other method as pressure measurement is around the room temperature and the molarity of the solution is used instead of molality as compared to other colligative property. Its magnitude is large even for a very dilute solution. The technique of osmotic pressure for determination of molar mass of solids is particularly useful for biomolecules as they are generally not stable at higher temperature and polymers have poor solubility. Two solutions having some osmotic pressure at a given temperature are called isotonic solution. When such solutions are separated by semi-permeable membrane, no osmosis occur between them. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% mass by volume sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cell in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt if the salt concentration is less than 0.9% mass by volume, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in this solution and they would swell. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentration salt solution loses water by osmosis and shrivel into pickle. Wilted flowers review when placed in fresh water. A carrot has become limp because of water loss into the atmosphere can be placed into the water making it firm once again. Water will move into the cells through osmosis when placed in water containing less than 0.9% mass by volume salt. Blood cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in tissue cells and intermolecular space because of osmosis. The resulting puffiness or swelling is called edema. Water movement from soil into plant roots and subsequently into upper portion of the plant is partly due to osmosis. The prevention of meat by salting and of fruits by adding sugar protect against bacterial action. Through the process of osmosis, a bacterium unsalted meat or candied fruit loses water, shrivel and dies. Reverse osmosis and water purification. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is now the pure solvent flow out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis and is of great practical utility. Reverse osmosis is used in distillation, desalination of seawater. A cymatic setup for the process is shown in figure 1.11. When pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membrane are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable spot. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days many countries use desalination plants to meet their potable water requirement. Abnormal molar mass. We know that any compound, when dissolved in water, dissociate into cation and anion. For example, if we dissolve 1 mole of KCl 74.5 gram in water, we accept 1 mole each of K positive and Cl negative ion to be released in the solution. If this happens, there would be 2 mole of particles in the solution. If we ignore interionic attraction, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.5 to Kelvin is equal to 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of two mole particles is 74.5 gram and the mass of 1 mole of KCl would be 370.25 gram. This brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecules of ethonic acid, acetic acid dimers in benzene due to hydrogen bonding. This normally happens in solvent of low dielectric constant. In the case of number of particles reduced due to dimerization, association of molecule is depicted as follows. It can be undoubtedly stated here that if all the molecules of ethonic acid associate in benzene, then delta Tb or delta Tf for ethonic acid will be half of the normal value. The molar mass calculated on the basis of this delta Tb or delta Tf will therefore be twice the expected value. Such a molar mass that is either lower or higher than the expected or normal value is called as abnormal. Normal value is called as abnormal value. In 80 want of factor introduce a factor is known as want of factor to account for the extent of dissociation or association. This factor I is defined as I is equal to normal molar mass divided by abnormal molar mass is equal to observed colligative property divided by calculated colligative property. I is equal to total number of mole of particle after association, dissociation, number of mole of particle before association or dissociation. Here, abnormal molar mass is the experimentally determined molar mass and colligative property are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, the value of I for aqueous KCl solution is close to 2, while the value for ethonic acid in benzene is nearly 0.5. Inclusion of want factor modify the equation for colligative property as follows. Relative lowering of vapor pressure of solvent P01 minus P1 divided by P01 is equal to I into N2 by me N1. Elevation of boiling point delta TB is equal to I Kb into M. Depression of freezing point delta Tf is equal to I into Kf into M. Osmotic pressure of solution pi is equal to I N2 R2 divided by V. Table 1.4 depicts value of the factor I for several strong electrolytes for KCl, NaCl and MgSO4. I value approach 2 as the solution become very dilute. As expected, the value I gets close to 3,4 K2SO4.